At this point, you may want to take some time to write a working class on your own. Typically, when I'm learning a new language, there are a few small exercises I like to write in order to get a better feel for the language I'm learning. This is one of those exercises. I call it NumWords. NumWords is a class that converts numbers into words. Here I have a working copy of all the files associated with the NumWords class from Chapter 4 of the exercise files. So this is a simple test program that uses the NumWord class. And you see I include the numword.h file, and there's a numword.h file and a numword.cpp file. The .h file has the class definition, which serves as an interface. The CPP file has the code that implements that interface. And we'll take a look at that in a little while. First, I want to show you the test case. I create an object of the NumWord class. I declare an integer value using this uint64 type, which is contained in the C standard int header file. uint64 is a type that's an unsigned integer 64 bits in length, and it's portable. When you use this type, you know that it's an unsigned 64-bit integer on any system that supports that type. And this is important because we're going to be dealing with some very large numbers here. And then I simply set n to a number, and I print it using this NumWords class. And I do this for a number of numbers, and then I have a loop that loops through everything from 0 to 200, and I print all of those. And so when I build and run this, you notice this is a very long output. We'll scroll all the way to the top. We start with n is 3, and it prints out the word 3. And then 47 and 73. You notice the hyphens here because those numbers are hyphenated in English. And then 1,492, 10,012, on and on and on and on and on. I set a maximum of this number here, which is 999 quadrillion, etc., all nines. And one larger than that, it prints out the word error because the number is too big and the class is not designed to handle numbers larger than that 99999 in the quadrillions. And then we count from 0, 1, 2, 3, blah, blah, blah. And then we get into the 20s and the 30s and all the way up here and 200. I wrote this test case to validate that the class does what it's supposed to do. Now, my implementation does this in English, and it uses English rules, or rather American rules, for how to write the numbers. And that's just the way that I've always done it. It might be interesting if I knew the rules in some other languages and how they differ to write a class that would work in multiple languages. Perhaps you can do that. But this is the version that I wrote, and we're going to be touring this code in a moment. But first, at this point, you may want to pause this movie and try writing this solution on your own. Take your time. You could even finish the course first and come back to this movie to see my solution. My version is in the exercise file, so you can refer to it at any time, but it's a really good idea for you to get your feet wet at this point and attempt to create a solution on your own with the tools you have so far. And now you're back, and I'm going to show you my solution. So we'll start with the header file. This is numword.h, and this is the header file that contains the class definition, and that's down here. There's class numword, and that is the interface for the solution. In practice, it's usually a really good idea to have your class definition in one file, typically with a .h extension, and your implementation in a .cpp file with all of the code. And that's considered best practice, and it really has some real advantages. And so if you do it that way, you'll see that that works well and it makes it easy to work with the code. So it starts up at the top here, and it includes a few libraries for using the C standard library, C strings, the standard int for defining that unsigned 64-bit integer type, and there's C math just for one constant that I use. I define a couple of preprocessor macros for the maximum size of a string and the maximum number that I'll allow. And then I declare a namespace, this namespace BW. You notice in my test code, when I use this class, I say BW : numword. I don't say using namespace BW because this is the only time that I'm actually using it. So I'm using namespace standard because printf is in there. But really, it's a good idea to use a namespace here because I'm declaring a bunch of constants in global space, and things like air_num and singles and these things, I don't want there to be name collisions with other classes. And so I use my own namespace for this. Now I declare some static constant strings for the words, and there's one for error, and then there's the singles 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the teens 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19, and then there's the tens, and you notice for 0 and 1, those would be errors because I have 10 defined over here and there is no 0 in tens, and then 20, 30, 40 on up to 90, and then I have 100, and then powers. And again, because I have 100 separately, the first one is error, and then I have 1,000, million, billion, trillion, quadrillion. That was as big as I decided to go. And we'll see how these get used a little bit later. I have a constant for the hyphen, and I have a constant for the space, and then I have rules in the code for when those get used. And then comes the class definition. So the number itself, there's a space for the number itself. It's a uint64 type, and then a pointer for the buffer, where we're going to build the words, and a counter for the length of the buffer, a hyphen flag, which is used for the compound numbers between 20 and 99 are hyphenated rather than using a space. So you don't say 24 with a space, you say 24 with a hyphen, or you see examples down here, 92, 73, 47, 23. These have hyphens, and yet there's spaces between 1,492. Then I have a few private methods that are not called from the outside. They're only called from within the class for initializing and clearing the buffer, for appending the space, and for appending buffers when I'm building compound words. And we'll see how those are used later. Then this is the public interface. There's a default constructor, which assigns a 0 to the number. There's a constructor where you can pass it a number, and there's the destructor. And then there's a setter for the number and a getter for the number. There's an operator overload for the copy operator. And then this is the real meat of it. There's words, and the one without a parameter will simply make words out of whatever number is stored in the number up here. Or the one that I use the most is words where I pass it a number. So that's really the header file. It's actually very simple. Now we'll go over to the implementation file. I have my destructor, which clears my buffer. I have the assignment operator, which sets a number and returns a number. And then I have the words method that doesn't take a parameter, and it calls the words method with a parameter with the number that's stored in the object. And then here's the convert to words. But before we get here, I just want to show you down at the bottom here, my initbuff and clearbuff. This is interesting because I'm not using the C++ standard library class for a string, which does a lot of this memory management on its own. I'm creating my own buffer and I'm clearing my own buffer. And I do this because I'm an old systems programmer, and this is actually faster and smaller code than bringing in the standard string library. If you want to use the standard string library, that's fine. And I think most people would probably do it that way. It's just a little bit bigger and a little bit slower, and it probably doesn't even matter. But for a lot of people, that might be easier. So here, when I initialize the buffer down here in the initbuff on line 92, first I call clearbuffer, which is just nice cleanup. And then I call malloc, which is the standard library function for allocating memory. Malloc, malloc, memory allocation. So malloc returns a pointer to a buffer that has that amount of space allocated. And then you notice that I set the first byte of that buffer to 0. And so I'm terminating that string right away. So I have a 0 length string that if for some reason somebody uses that, it will be a 0 length string and it won't create a buffer overflow. And I set my hyphen flag to false because this is really the initialization routine. And we're only going to use the hyphen flag in special cases. And so most of the time we're not using it. And then I have a couple of methods here which are used for building the string space. There's one that appends a space, and it checks the hyphen flag, and it appends either a hyphen or a space. And once it's appended a hyphen, it sets that hyphen flag back to false so that the next time it's called, it'll append a space unless the hyphen flag gets set again. And then this one here is for appending text to the string buffer. And again, this is a little bit complex because I'm doing this with C strings. If you're using the standard string library, it won't be this much work. I check to make sure that my string length is not too big, and I check for an error condition. And then down here, I actually do the copying, and I copy from one buffer into the other. I increase the length, and I set a terminating 0 at the end. And so that's actually pretty straightforward. It just looks a little bit complicated. So here's where the meat of the work is done. This is the words method. This is where I build the string of words from the number. And so it gets passed a number, and if the number's too big, it returns the error. I initialize the buffer. I initialize my internal copy of the number. And if it's 0, I simply pass a 0 and I return a 0 and our work is done. And if it's not, then I need to start at the largest possible number and work my way down. And so for each of these chunks, I'll build the word for that chunk, and then each of the chunks gets appended on and it builds the whole string. So this first part is for the powers of 1,000. And so it checks to see if the number is actually greater than 1,000. And if it is, then it starts at the highest possible power, the power of 5,000, and it works its way down thousands by thousands. And for each one of these, it calls itself, it strips out that part, and by dividing by the power, for example, if you have like 143 million, it'll divide out that million part, and it'll just take that 143, and it creates a new object, and it calls numword again, and that way that'll get passed down into the rest of it, and it can build that number recursively. And so this is actually a really, really useful use of recursion here. And it's limited because I can use recursion because I know it's not going to get out of hand. I'm only going to be recursing a few times at most. And so once I've built that, then I append a space and I append the buffer and I append another space and the word for the power. So this would be the word million, for example. And then I subtract out the part that I've already done and go back into the loop. And so that's how the powers of 1,000 are done. Then we come down here into the hundreds and it starts getting a lot simpler. Again, I divide out the hundreds. I call numword again for the smaller part of it. So if it's 300, this will get a 3. If it's 500, this will get a 5. And again, a space, the words itself, another space, and the word hundred. And then for the tens, this is the ones between 20 and 100. Once I divide that out, I have the hyphen flag. So if it's 20 and there's another number after it, it's going to be hyphenated. So if it's 21, 27, it'll get a hyphen. That's why the hyphen flag gets set here. And then the teens and the singles are very simple. I'm simply looking it up in the table, and that's really all there is to it. So for the teens and the singles, it's almost the same code. They're just pulling from different parts of the tables. So that's really it. That's the code. That's the solution that I came up with. What solution are you going to come up with? This is actually a useful real-world application. A class like this is typically used in banking applications for writing checks and other documents where monetary values are typically expressed in words.